Okay, exponential and logarithmic functions and expressions. We're going to start with an exponential function. An exponential function is a function of the form y equals b to the power x, where b is greater than 0. Here's the graph of y equals b to the x, where b is greater than 1. Okay, you've seen these, right? I mean, this is like last semester stuff, or perhaps last year. All right, so let's take a look. Using this graph, complete the following limits. What is the limit as x approaches 0 of b of x? Looks like 1. What is the limit as x goes to infinity of b to the x? Infinity. What is the limit as x approaches negative infinity? Or really, I think technically you're supposed to say the limit of b to the x as x approaches negative infinity is 0. Is it ever 0? No. But it's going to approach 0, right? So what we basically say is we can get as close to 0. We make x large enough in a negative direction. So, take a large enough negative number, we can get as close to 0 as we want. Right? And all of that goes into the whole epsilon delta, which is the formal definition of limits. And if you do calc next year, you're probably going to get into that formal definition, right? We don't. So we're a little more informal. It's high school. The graph of y equals b to the x, where b is between 0 and 1, right? So we know that this is what kind of an exponential function? Yeah, growth, right? It's exponential growth, and this is decay, right? Good. You remember something from... And decay occurs when b value is between 0 and 1, right? So we've got a half, we do half-life stuff, and a third, a quarter, whatever. Use the graph above. So the limit as x approaches 0, b to the x is 1. The limit as x approaches positive infinity is 0. And the limit as x approaches negative infinity is infinity. And beyond. That's Buzz Lightyear. I've got to dig up a Buzz Lightyear. To infinity and beyond. Complete the following tables for y equals b to the x, where b is greater than 0. So, domain of the exponential function where b is greater than 0 is x belongs to the reals. So, how do we want that nice form? So, we can do it two ways, right? The set of all x such that x belongs to the reals, or I like the bracket notation, right? Which would just be negative infinity to infinity, right? So personally, I like this. It's better, right? And especially when we're looking, as you're not doing this x is greater than or equal to 2 stuff, right? You just go 2 to infinity, right? Do I include it or not? Well, we know it's a square bracket or a round bracket. So, and the range is y is greater than 0 or 0 to infinity with a round bracket which says does not include, right? Square bracket says doesn't. The x-intercepts. There are none, right? No x-intercepts. What are we going to write? None. None sounds good. The y-intercept. 1. The horizontal asymptote. Yeah, you need an equation, right? So it's y equals 0. Okay, so that is the characteristics of y equals b to the x, where b is greater than 0. Okay, so whether b is between 0 and 1 or greater than 1, still the same character, right? We have the same y-intercept. We have the same horizontal asymptote. We know there's behavior. This is decay, so it's going down. This is growth. It's increasing. State the limit of each of these. State the value of each limit. So what's our first strategy in doing limits? Try subbing it in, right? Just substitute in the value, see what happens. All right, so this will be equal to 3 to the 4 minus 4, which is 3 to the 0. Can you do that?
1.
Well, I can. What is it? 1. Yeah, so I don't even have the, you can't do that clip. You can't do that clip is not up, so So you can't give me anything we can't do, because I won't be able to. Okay, the limit as x approaches 0 from above, positive, right? So as x approaches, that means you're going from right to left. Okay, so you're approaching 0, but your values of x are positive. So, all right, you know what? Let's just try substitute. Well, okay, can we put 0 in there? No. Okay, you can't do that, right? Sorry, I don't have to click. So what can we do? Well, we can put in a small number. Give me a number we can put in for x. 1. Really? Come on, you can do better than that. Can you get closer to 0 than 1?
0, 1.
Okay, well, let's not go quite to that extreme, but let's go like 0.001, okay? So we're just going to try it. What we want to do is see where's it going, okay? So we're just going to do this kind of a thought experiment. If I put in, okay, so if I put in 4 to the 1 over 0.001, so what is 1 divided by 0.001? So it's 1,000, right? And if we put in 0.0001, then that would be bigger, be 10,000 or 100,000. I forget how many zeros there were. But what can we say about this number here? This number is going to be large and positive or negative? In charge. And the charge on this number is positive charge or negative charge? It's going to be positive. So we are going to get a large positive number because we are approaching 0 from above, which means that x has to be positive. The smaller x gets, the larger 1 over x gets, which means that we can think of this as being 4. Let's say leads to. So 4 to 1,000, right? Or we're going to say it's 4 to a large positive number. What is 4 to the power of a large positive number?
Big number.
Big number. Well, how do we say big number?
Infinity.
Infinity. Okay, so the closer that we get to 0 from the positive side, the larger 1 over x gets, but is positive. So we have 4 to a really large positive number, like 100 trillion, and that's going to be even bigger, so it's going to be positive infinity. The limit as x approaches 0 from below. So from below means you are going from right to left. Okay? So give me an example of a number that's close to 0 and yet below. So let's say we use the same number, 0.001, but we're coming from below. Below 0 is negative. So we've got 4 to the 1 over negative 0.001. So what's this? So it's 4 to the power of what? A large negative number. Okay, so what's going to happen when that happens? Well, so we had 4, so we imagine this is 4 to the x, and we say putting in, you're getting, okay, what were we doing? Which one are we using here? Hang on. So, yeah, 4 to the 1 over x. That doesn't even apply. No, never mind. Forget that. What's 4 to a large negative number? So negative 1,000, right? That's going to be 1 over 4 to the 1,000. So 4 to the 1,000 would be really large. You have 1 over a really large number, which is 0. Okay? So as x approaches 0 from below, the limit of 4 to the 1 over x, as x approaches 0 from below, will be 0. Okay, so you can just think of these as, I'm going to throw in a number. What's that number going to be? So let's try this one. We got x approaches negative 3 from below. So give me a number that's really close to -3, but is below it. Yeah, well, I don't know how your number line looks, but on my number line, if we're coming at -3 from below, it means we have to be a little bit, magnitude's a little bit larger, so we'll go with, like, if we stick with the theme of 0.001, what number am I going to use? So -3.001 plus 3, right? So we are approaching -3, right? -3 from below -3, which means we have to be lower than. So 2.999 is not lower than -3, it's higher, right? It's closer to 0. Okay, so that's going to give me 1/2 to the power of, what do we got down here? 1/2 to the power of -1.001. And what's that going to be? Well, it's a half to this is going to be a large negative, right? So it's 1/2 to a large negative number. Okay, so can we go, let's go back here. So this would be the one where we have a half. We're having a large negative number. So where's this going? To infinity, right? To positive infinity. Okay, what do I mean to do? Oh, yeah, the other one, yeah, I know, now I know what I meant. So 4 to the 1 over x, so we had 4 to a large negative number, we're going this way, that was the 0, right? 4 to a large positive is this, so 1/2 to a large negative is infinity, 1/2 to a large positive would be 0. Okay, and that's going to infinity. Okay, any questions, comments, or concerns on that page?
Do we have b being negative and negative value?
No, so b can't be negative, right? Base of an exponential function must be greater than 0. Logarithmic functions. What is the inverse of y equals 3 to the x in exponential form? So to get the inverse, what do you do with x and y? You switch them. So what are we going to write? X equals 3 to the y. Okay. Now we don't like that. We like our functions to be y equals. So to do that, we created something called a logarithm. So how do I change this into logarithmic form? It becomes well, they're having more fun than we are. Y equals log base 3 of x. Okay, so that is the logarithmic equivalent of, right, the inverse of the exponential function, written in the form y equals. So the inverse of y equals b to the x is y is equal to log base b. Notice the bases are the same, right? Base of the exponential function, base of the log. B has to be greater than 0. Okay, so we can't do negatives. Can't have a negative base. Here's the graph of y equals log base b of x, where b is greater than 1. Here's the graph of y equals log base b of x, where b is between 0 and 1. They're just reflections in the line y equals x of the exponential function, right? So if we took the exponential function reflected in the line y equals x, we're going to get this. Use graph above to complete. The limit as x approaches infinity is infinity. Okay. I can't go that far. The limit as x approaches 0 from the positive side is negative infinity, where b is greater than 1. If b is between 0 and 1, we have a base of like a half or something, right? Use the graph above to complete the following limits. The limit as x approaches infinity is negative infinity. And the limit as x approaches 0 from above, because you can't go to 0 from below, you can't go to 0, right? We just can't do, is infinity. Okay, wait a sec. This is infinity? Oh wait, what did you say? Negative infinity. Okay, so that's then that's what I should write. You're supposed to correct me. This is calculus. We cannot let an error go uncorrected. It'll be like 4 boards later, and we'll be scrolling up through 4 boards and say, oh, 2 plus 2 is 4. And we have to redo 4 boards worth of work. Okay. Complete the following table for y equals log base b of x where b is greater than 0. The domain is x is greater than 0. Greater than or equal to, or just greater than? Or, in the nice notation, 0, infinity, right? The range is elements of the reals, or negative infinity to infinity, which always uses round brackets, right? Infinity, always round. And the x-intercept, or x-intercepts, 1. The y-intercept, none. X-intercept, 1. Vertical asymptote, x equals 0. Remember, an asymptote is a line, and a line has an equation. You don't just write 0 in there. You write x equals 0, right? Asymptotes are lines. Lines have equations. Okay. Any questions? Comments? Concerns? Moving on. State the value of each limit. Okay, so what should we try doing? What is that? 5 from above? It looks like it.
Yeah.
Okay. Can be. It's a little fuzzy. All right, so we stick a 5 in there. We have log base 2 of 0. You can't do that, but we can. So we want to get close to 0. So we are going to have the limit as x approaches 5 plus of log base 2. So if I put in a number that's above 5 but is approaching 5, what's the number that's above 5 approaching 5? So it's going to be a small, what kind of number? Small positive number, right? That's what we're looking for, right? So this is going to be a small positive number. So I have the log base 2 of a small positive number. Wow. Let's try that again. And what is the log base 2 of a small positive number? Go back here. Log base 2, small positive number is negative infinity. Actually, get rid of that limit. Just right, yeah. So it's log base 2 of a small positive number, which is negative infinity. Approaches 4 from below. What's a number below 4, but close? 3.999. When you go 4 minus 3.999, what do you get? Small positive number, right? Okay, so this is log base 1/2 of a small positive. So now we have to think, what does log base 1/2 look like? Looks like this. So a small positive number goes where? Positive infinity. Okay, so we just go back, we look at this graph. You can graph that, right? You can always, well, if you could use a calculator, you could throw, otherwise you're actually going to have to know some stuff. So which is infinity. And what's next? State the domain of y equals log base 3 of 5 minus 2x. So what do we know about 5 minus 2x? What does it have to do or be here? It's got to be greater than 0, right? Okay, so we're going to say 5 minus 2x. Okay, so I know logs. I know you cannot take the log of a negative, nor can you take the log of 0. So we can say, all right, using some knowledge of logs, we know that 5 minus 2x must be greater than 0. Now, you know, there's no point moving the x over there. Like on an equal sign, I would move the x over there and then just flip sides. But you can't really do that with inequalities. So we'll go negative 2x is greater than negative 5. Nice 5. Negative 5. So then we go x dividing by negative 2. What do we do with the inequality? We switch it. So it becomes x is less than 5 halves. Okay, so we say set of all x such that x is less than 5 halves. Oops. I'm mixing my metaphors. I'm trying to draw a brace bracket there. Or negative infinity to 5 halves, right? Using the parenthesis notation. Right. Make sense?
Question. So for, like, you just put in a small positive, say for A.
Mm-hmm.
So like if you actually do it out and then you get like log 2 point, say 0.001, and then 2 to 0.001, why isn't it 0?
So let's say
Like,
you
the
had,
graph that I was looking at my sheet.
let's say you had a calc. So whether it's log 2 or log 10 won't really matter, right? So I can just do log because somewhere on here there is the base thing for logs, but I just don't know how to get there. It's like,
So how does the math go?
press the math button.
Press up.
Which one?
Up.
Up.
One more.
Oh, log base. Oh, okay, hang on, I gotta get rid of that first log. Math. Log base, okay, log base 2, what do we want? A small positive number? 0.000. Let's just hammer in a few of them. Negative 19, so that's large negative. Okay, so did we say it was going to be negative infinity? Yep. Okay, so you want to get closer.
So how do we know, like, we don't have a calculator, so.
Yeah, you got to know that. So you have to know what the graph looks like. Okay. What is the graph of log? What does a log graph look like if b is greater than 0? Right. So you got to say, okay, it looks like this. Okay. Now, I mean, in the sense, you can kind of figure it out, right? You can just sort of go back to, you know, I know what log, like log base 10 of 10 is 1. So when x is 10, y is 1. When x is 100, y is 2. It doesn't get all that big that fast, but you know, you got to go to 1,000 to get 3 and so on. But that tells me that it's going like this, right? That I know it's going up like that, and therefore it has to go down like that.
Okay.
Okay. And then the other one really is just, I mean, in essence, all you're doing here is, you know, reflecting it, right? Just a reflection in the x-axis. You think of, you know, if that's 2, then this could be like 2 to the negative 1. So a half is 2 to the negative 1. So it's a negative x and reflection in the axis. Right. Okay. Is this max? Exponential and logarithmic expressions use the fact that y equals b to the x is equivalent to log base b of y to complete. So this is exponential. 2 cubed is 8. So I write what? Log base 2 of is 3. Okay, if I have log base 3 of 1 over 81 equals negative 4, then in exponential form, what's my base? Okay, base is the base, right? What's my exponent? Negative 4. Remember, a log is an exponent. That's all a log is. I mean, you learned that last semester or year, right? What's a logarithm? It's an exponent. What exponent? It's the exponent you raise the base, whatever, to, see, right here. Note that log base 2a is the exponent that you raise the base 2 I always think we should never use 2 in that. You know, it should be like log base 3 of 27. So it's the exponent that you raise the base 2 in order to get 8. Watch, this thing disappeared. Okay, evaluate log base 5. So 5 to the what gives you 625? What? I mean, 5 squared is 25, 5 cubed is not quite yet 625, so then we should probably go one more. I'm going with 4. 4. 5 to the 25 is like really big. How big is it? I don't know. How big is it? 5. Yeah, 2.9. That's just a little larger than 625. 7 to the what gives you 1 over 49. Negative 2. Hang on, I'm on the right page. B to the what gives you 1. Yeah, anything to the what gives you 1, right? 0. The log base 2 of 2 to the 8th is 8. That's the easy one, right? 2 to the what gives you 2 to the 8th? Wait, let me think. B to the what gives you b to the x? X. And then the most famous of them all, b to the log base b of x is x. Get that one figured out. At some point last semester, you figured that one out, right? See? So the exponent that I raised the base b2 to get b to the x is, right, x. That whole, right? So like 2 to the log base 2 of 5 is just 5. Right? Okay. Man, stuff is changing. Laws of logs. Please the following statement. So the log base b of x to y, the log of a product is equal to the sum of the logs. It's been a while, has it?
Yeah.
I thought we could forget all that after the diploma. Yeah, it's not even on your sheet. The log of a quotient is equal to the... Yeah, if that's the sum, then...
That's the word.
So what do I write next? Minus. Log of a power is like the most useful one, right? Allows us to actually solve for unknown exponents. So what's this equal to? And, right, that's how we solve for, wow, everything's changed. And we can watch it happen in real time, or with a slight delay. Expand, log base 3 of x squared y over 9z. So using the laws of logs. What do we write? So it's going to be log base 3 of, so what's first? X squared, okay, x squared. Then what do I do with the y? Or do we want to, well, I don't know. I'm looking at 2 different things here. All right, here, let's do this. So let's just take it. Here we got a quotient, right? So we're just going to take the numerator. We'll do the log of the numerator minus the log of the denominator. Okay. Then we will apply. I'm just going to go this way because I might run out of room if I keep going down. So generally speaking, don't do this. Right? Just for illustrative purposes only. So it's log base 3 of x squared, right? So we're going to split it out. We have a product. So what's that become? Plus, okay, then what? Minus, bracket. So let's split this out, but we'll do it in brackets, right? So log base 3 of 9 plus log base 3 of z. Okay, keep going. Equals. I'm just going to come back over here because I think I need 2 more. So what do I do with the 2? Put in the front. So 2 log base 3x plus, there's nothing really you can do with log base 3 of y, right? I mean, it is what it is. So log base 3 of y. And then we have minus log base 3 of 9. What's another way to say log base 3 of 9? 2. Right, because 9 happens to be power of 2. So minus 2, and then what do we do with this log 3z? Minus, again, right? So the minus distributes, right? So minus log 3z. You could have got there in one step, really, right? Like, I don't know how much I would have objected. I think it's kind of laws of log-y stuff. Okay. It's like x squared, so it's 2, 2 log 3x plus log 3y minus log 3,9, which is 2 minus log 3z. All right, so that's taking a single log and expanding it. What if we have an expanded? We want to express this as a single log. So what's the first step with this guy? So log base 2 of, or should it be 3 log base 2? No. What do I want to do with the 3?
Put it as the exponent.
Right. So log base 2 of x cubed minus what? Y to the 4th? Okay, so we need to combine this into a single log. Go ahead, you can do this one more step. Come up with the answer. The hint should look something like this. Subtraction becomes division. Okay, so the x cubed, that's x cubed. And where does the y to the 4th go? On the bottom. Where does the z go? Also on the bottom, right? So it's log base 4 of x cubed over y to the 4th z, right? So if we see numbers in front of logs, we want to use the laws. The laws only work if you're taking the log of something, not 2 times the log of something, right? So to use the laws, you have to get rid of any numbers in front. They need to be moved up out of power. Yep. Sure. Evaluate 1/2 log base 3 144 minus log. So evaluate says come up with a value for, right? So in other words, this should work out to a number which is probably doable without a calculator. So, well, it's square root of 144, which is 12. So, go ahead, do it. You can do this. I will give you a 10-second lead time, and then I'll start writing. So you can write this. Right? Just start off. So Rebecca, where's the half go? So where's the half go?
Exponent.
Where's the 2 go? Where's 2 go? Exponent. What's 144 to the half? 12. Actually, yeah, wait a sec. Yeah, just leave that. What's log base 3 of 27? That's easy, right? Who wants to square 27, right? I don't want to square 27. So log base 3 of 27 is 3, and 2 times 3 is 6. That'll make life a little bit easier. And that's equal to log base 3 of what? 12 over 4, right? Which is equal to log base 3 of? Which is equal to? Okay, so 27 squared. That was dumb. Don't do that, because log base 3 of 27. We can evaluate. That's easy, right? That's just 3. 27 squared, that's like 3. It's like 729, and then you got to figure out what power of 3 729. You don't have a calculator, so that's a little tougher. So evaluate when you can. I guess that's the moral of that story. Drop 2 files with changes. Solve. Express your answer as an exact value. How do we solve a logarithmic, whatever this is? Oh, sorry, an exponential. How do we solve an exponential equation? Log. Log what? Log numbers. Okay, I logged one side. What do I do to the other side?
Log it.
Log it as well. Now what?
Bring the x to the front.
Yeah, just log 6 over.
So I don't know about you, but if I'm solving this, this is generally the next line I write. I just write x log 5 is log 6 because I'm kind of lazy and like I know. But, so either one, right? You could do this. Look, I'm taking the log of both sides. Oh, now I'm using that power law to move the x in front. But I usually just go from this straight to this. What's x?
Log 6 over log 5.
Is that exact?
Yeah.
Yeah. Okay. That's an exact value, right? Whatever that actually evaluates to is not an exact value, right? It's some decimal. Yeah.
So it's log base 5.
Log base 5 of 6. Is that what you want to do? Okay, if I had to evaluate this with an old calculator, this is easier. If you have the newer firmware, you can do this. I don't think TI-83s have that log, do they?
No.
They don't have that log base thing, right?
No.
Okay. Because actually, this version of the 84, somewhere there's a function, I don't even know what you push. But like one of these, something, or maybe you go alpha this. Ah, there we go. Okay, so you push alpha. Oh wait, I can't actually.
Like F2,
Okay, so alpha. There, log base. There's log base. Okay, so if you hit alpha on this, you'll get into the different menus. Oh, hey, I did not know that. That's actually useful. Okay. Like to get y1, right? Otherwise you're going bars, y bars, arrow over the function, you go enter twice. Didn't know you could do that. What's this one do? Apparently nothing. What's that one do? Wait, I'm not hitting alpha now. I put a dot on there. Okay, apparently nothing. That does the y variables. Whoops. That does... whatever. Anyways, we don't even have calculators, so yes, they're the same. Okay, what do we do with 4? Is it 2x plus 3 equals 10? Take the log of both sides. So just to be all nice and formal, I'll do this. So then we go 2x plus 3. Now, the important thing is, when the exponent is an expression, you're going to bring it down in parentheses, right? What's that equal to? 1, right? Because log of 10. Because what base is this?
It's
Base 10. What base should it be? It could be any base you want, really, right? So, I mean, if that was 7, you could just do a log base 7, and then that would be a 1, but then you're stuck with a log base 7, and that's not so easy to use on the calculator. Why do we do base 10 logs? Because calculators have base 10 logs. All right, now what? Okay, so I guess we got to divide both sides by log 4, and then subtract 3, and then divide everything by 2. Okay, so do that. Divide both sides by log 4. And then subtract 3. And then divide by 2. Just looking at this, we're going to have... Yeah, you know what? Instead of that, let's do this. So let's expand this, then we just get to subtract that way we won't have fractions and have to worry about getting a common denominator to get it all into one thing. So now we can just go like 2x log 4 is 1 minus 3 log 4. And so x is 1 minus 3 log 4 over 2 log 4. Okay. It was like easier to go that way than what if I divide both sides by log 4, because then I would have to get the common denominator and try and add them, and yeah. Why do we even use the change of base formula anymore? Your calculators all do this. Well, because if you have an old calculator that does not do log base 3s, right, then you got to use the change of base formula. So how would you evaluate log base 3 of 20? Yes, you can use your calculator on a calculator using the base change formula. Right. Okay. So log base 3 of 20. So in this case, 3 is a and b is 20. So log 20 divided by log 3. Yeah. I don't know if it's how many. Do you save any keystrokes really? You're going to go log, then you'd have to go down there and put in 3.
There's just less brackets.
Go up. Yeah, less brackets. So, okay. Quit. So we go log 20 close bracket divided by log 3. So that really says 3 to the what is 20. So the number is between what and what? Between 2 and 3, right? Because 3 squared is 9 and 3 cubed is 27. So as long as I get a value, I add 2.72. What did it say around the nearest hundredth? 2.7 what? 2.73. Okay, questions, comments? Ready to move on? Ready to move on. The sooner we get this done, the sooner you get on to homework. Use your graphing calculator to determine the value of each limit rounded to the nearest hundredth. So, okay, we're going to use graphing calculator. Let's just slide this over. I'm going to go to y equals. I'm going to type in that. So we want b to be 2, right? So we're going to go 2 to the x minus 1. So let's throw a bracket down. Go 2 to the x minus 1 divided by x. Okay? Now we could just hit graph and see what happens. All right. So, okay. And we want to know what happens. So we could go second calc value 0, and what's going to happen? Well, you don't get an answer because then, hey, you're trying to divide by 0, right? Can't really do that. So you can't do that. I don't have it. So, but we can look at values close, right? So let's do this. Let's look in close on there. So let's adjust our window, and we will use a window of -1 to 1 by 0.2s, right? This way when we're looking at it, we can say it's 0.2, 0.4, 0.6. And the y values, well, we know we're above, right? So we can start with a minimum y value of 0. So let's go from 0 to 2, also by 0.2s. Okay, and now we can hit graph. And so we're going to say that this limit is what? That's 0.2, 0.4, 0.6, 0.8. So what is this? Value here. About 0.7. Okay, so let's say 0.7. Now, you might say, let's take a look at this, right? So we're going to say, let's go to second table set. So you can set up the table, right? So we're saying, well, we want to look around 0. So let's go, let's say maybe 0.3 by 0.01. What will that do? And we say, go look in the table. Should start at x. Okay. Well, it should have started my x like negative 0.03. Okay, so negative point. So as we approach 0 by hundreds, we got 0.68, 0.69, 0.69. So 0.7. Yeah, that's 0.69 something. Okay, 0.7 is good. What if b is 2.5? So we're just going to go here. We're going to go second function insert, right? So I'm going to put in a 0.5. So now I got 2.5 to the x, right? And we can graph that. Okay, what do we got? 0.2, 0.4, 0.6, 0.8, 1. So what's that? 0.9. Okay, let's go look in the table. 0.9, 0.9. Let's say 0.9. Close. To the nearest tenth, anyways. And what do we want to do? We want b to be 3. So we're going to go here 3. So at this point, you could just go 0.0, or you could delete these two. So you could go delete, delete, delete. Okay, so there's 3 to the x. Graph that. 0.2, 0.4, 0.6, 0.8, 1, 1.2. This is around 1.1. Okay, go into the table. Yeah, okay, 1.1, close. Now, what if I were to tell you there exists a value of b such that, or so that, the limit as h approaches 0, b to the h minus 1 over h is equal to 1, right? So we found 2 was 0.7, 2.5 was 0.9, 3 was 1.1. We call this value e for Euler's number, probably because he, or Euler, however you pronounce it, because he probably found it, I guess. So e is the value such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. So how are we going to figure out the value of e? Where should we be looking? So what number might I try next?
2.75.
2.7, yeah, that's called a binary search. Binary search, just go halfway, right? It's like, okay, that's too small, that's too big, and that's 0.9, that's 1.1, go halfway. Second, no, y equals, okay, so 2, and we got to insert, right, 0.75. That's just a smidge high. You see, just a little bit high. Look in the table, yeah, not much. So what do you want to do next? Let's throw that in. Yeah, it's getting a lot closer. Yeah, like we're getting pretty close. Okay, so the value of e actually, so you got two things. You got an e key down here, you got a pi key, you got an e key. E and pi, very important numbers, right? I didn't even know. This got pointed out to me today, so today I discovered the e key. So you can hit this, and it'll give you the value of e, which is 2.7182818245904523536, which if you actually want to see that number. Hold on. Okay, so to the nearest hundredth, yeah, it'd be 2.72. And it's really 2.718. It's known as the limit of natural growth, this value e. It's important in calculus. So this 2.72. What is lnx?
Natural log.
Yeah, the natural logarithm. It's the logarithm base e. Mostly I will say it as ln instead of ln, unless you're a fan of ln, and then you could say ln.
I love Ellen.
Well, there you go, then you're going to say ln. I'm going to say ln, although I hate mowing them, so maybe I should say ln. I'll have half the year I don't have to. So. Okay, so what is ln x or ln x? Most of the time I'm going to say ln. The inverse of y equals e to the x is, what do we do with the x and y? Which can also be expressed in logarithmic form as y equals log base e of x. Another expression for log base e of x is ln of x, which is read as ln x or the natural log. Okay, so it's used a lot. It's on your calculator. See, ln, right below log. Did you guys look at it at all in 30-1? We actually look at it in 30-2, right? Sort of say, hey, this is natural log. This is what it is. I know, right? It's like they actually do statistics in like 20-2, and you guys don't do stats anymore. So yeah, it's a weird world. I don't know. So in other words, the exponential function y equals e to the x and the logarithmic function y equals ln x, which is log base e of x, are inverses of each other. Sketch the graphs of y equals e to the x and y equals ln of x on the axes below. So this is just basically an exponential function, right? So it's got the characteristic, the y-intercept, which is when x is 0, is 1. The base e is bigger than 1, so it's an increasing function, or it's a growth, exponential growth. And this is just basically a log function. And that's what log functions look like. Okay, but I guess we could put like a 1 there, and a 1 there. And that's y equals ln x. And they have some very important characteristics which we will study a lot of. And we're done.